All right, so we have been solving this problem. We haven't started solving yet. So let's see this problem. So this is just a constant acceleration motion of an object. So there's an initial velocity is given, acceleration is given. And the first question asked is the displacement of the object when it is at the farthest point on the left, right? And then in parts B and C, yeah, I have some problem with the, remember, yeah. So second part is about the time when the object passes from the same point. And I'm asking for the time when this happens and the velocity when this happens. So I think there are too many lessons in that problem. But in any case, so let's start with part A. So as I have said, initially the object is moving towards left. Let's say it like this. So initial velocity was like that. But that means since the acceleration is towards right, the velocity is going to change in the rightward direction. So that means this velocity gradually will become like that. At some point, the velocity will become 0, and then it will turn right, right? So if I translate all of this into motion, then that corresponds to, let me erase everything in here, a motion where the object actually moves and then turns back from some point on the left. So let me draw it like that in here. So the motion is somewhat like that. Okay. It's V0. Okay, so in any case, so as a result, there's some kind of a condition in here that expresses the fact that the object has reached to the farthest point on the left. And the condition is that the velocity becomes 0, right? So let me just say it like this. Let's just write this thing down like that. So the instantaneous velocity at the point where it turns is basically is equal to 0. So turning point of the motion is a point where the position is a max or a minimum, right? A turning point is the same thing as this one. Let me just write it down like that, right? That's equivalent to that one. So that equivalents to a point where the instantaneous velocity is equal to 0, right? Let's just keep this in mind. Okay. So in any case, so I mean, there's some kind of a condition that expresses this final point, and we just express it in the as an equation in here, as some kind of a value for some variable, right? So in that case, it corresponds to velocity being equal to 0. So it's asking this question in here. So what's the displacement when the velocity is equal to 0? So what are known? I know the acceleration. Do I know the final velocity? No, I don't. So as a result, I know the acceleration. I know the final velocity, sorry. I know the final velocity, and I need to find delta x, right? So as a result, I need to use a formula that relates displacement, final velocity, and acceleration to each other. Okay, I mean, that's how I'm thinking about it. Of course, when I'm solving problems, I'm not going to explain it like that. But there's some kind of a formula that relates these three to each other, right? Otherwise, if I don't, sorry about that. There's something else in here. Sorry. Final time, that's the one that I don't know, all right? So I know the final velocity. I know the acceleration, which is also the same as the final acceleration. I don't know what the displacement is, and that's the one I need to find. I don't want to find the final time. Okay. So as a result, I just find a formula that relates all of them to each other. And the formula is this. It's 2a times delta x. Okay. Can you solve the problem without using this formula? Yes, you can, but in that case, you need to find this variable that I said I don't need. Okay, so that's the difficulty in there. Well, it's not that terrible difficulty, of course. So if you have time, if you're clear about what you're doing, then that's okay as well. Okay, so but let's just go ahead and solve this like that. So final velocity is 0, initial velocity is -6, and just keep in mind that I actually write down. I don't write down the units in here when I'm in the middle of the computation, because that's going to take too much time. So acceleration is positive, it's 2 meters per second squared. And then I need to multiply this with delta x, okay? Just keep in mind that I just write down the correct values in here, correct components, because otherwise I would have some kind of a problem in here. In any case, the left-hand side is -36, the right-hand side is plus 4 times delta x. So therefore, delta x is equal to -9 meters in here, all right? In the reference frame that I have chosen, then the displacement would be -9 meters. Okay, before passing to parts B and C, so let me solve the problem again in the way that I have promised. I'm going to choose the reference frame in the other way, right? So I have chosen the reference frame, the x-axis pointing towards right. Now I'm going to choose it pointing towards left. Why do I do this? Well, it's the solution of the same problem, but I mean, it is this idea in here that in a different reference frame, I'm going to use different numbers, but still I get the same physical solution. So I get different mathematical numbers, but I get the same physical solution. So initial velocity is, so in that case, the x-axis is pointing to the left. To the left. Initial velocity is this time positive, and the acceleration is this time negative. Okay, so let's just compare these with this one. All right, so let me just do it like that. All right, so velocity is still the same, the acceleration is still the same, so they are in the same direction. So the vectors are the same, but the reference frame has changed from right to left, and as a result, the initial velocity and the acceleration have changed values. So I'm expressing the same quantities with different numbers now. Okay, just keep this in mind. So again, right, I'll just concentrate on this. How do I solve this? Yeah, I'm going to use the same equation now. V squared minus V0 squared is equal to 2a delta x. So the final velocity is 0. Initial velocity is +6. Acceleration was -2 and delta x. So as a result, we get -36 on the left-hand side and -4 delta x on the right-hand side. And the displacement is +9 meters. Okay. So in both cases, therefore, if I show it with an exaggerated thing like that, so I would find the displacement to be the same. But in this reference frame, it appears like +9 meters. In the previous problem, I found it as -9 meters, which corresponds to this one again. Okay, so let me demagnify, right? So the same physics, but different numbers, right? So in these two solutions, therefore, I use different numbers, but I still express the same thing, okay? So the lesson in here is this. I mean, I'm going to come back to this later because this is the basis of the relativity principle in a way, because you can view the same physical phenomenon from different reference frames, and the phenomenon is going to look quite different to different people, but the same thing is happening, right? You're describing the same things with different words, with different numbers and whatever. So this is one of the important things, okay? So there's, I mean, I'm also going to object to some of the conceptual problems of students, most of the students, some of the students, let's say. They tend to distinguish this part of the motion where the object is moving towards left from that part of the motion where the object is moving towards right. But there's no difference between them except that the velocity has a different direction in these two parts in here. But still, the acceleration is the same. So at that point, for example, where the object stops, the acceleration is still same at that point, for example. But somehow people actually try to separate these mentally. So as a result, they divide the motion into these two parts. But if you look at this problem from these different reference frames, I mean, it might appear that that point may not be a very special point according to some other people, okay? This is going to be clear later when we talk about the reference frames. But let's pass to the part B. So after how many seconds does the object pass from the initial point, right? And right, I'm asking for the time. I'm asking for the time here, and I'm asking for the velocity for the part C. Okay. All right. Part B. Why do I do this? No. Part B. All right. Part B. So it is, let me show it like that. It is this point in the motion. So it is that point in here. And I need to express the condition in here. Condition for that point is basically the object is passing from the same point. So therefore, the displacement is equal to 0. In the real world, it is possible to move. Yeah, it is possible. Is it possible to move towards left with an acceleration towards right? Yes, it is possible. Right, let me state this. Okay, so condition. So the condition of that point is delta x is equal to 0. In part B, I'm asking for the time. And in part C, I will be asking for the velocity. All right. But I mean, let's just concentrate on this, right? So I'm just going to think of it in the same way, right? So I have position, velocity, acceleration, and time as the final quantities. So I'm asking for the value of this one. I know what the acceleration is, so this is known. I know the position, that's also known. So as a result, I need to find a relationship that relates position, acceleration, and time to each other. It shouldn't, I mean, that relationship should not involve the velocity, right? I know just the ideal relationship in here. So it's that relationship. So it's x is equal to x0 plus v0t plus 1/2 of a times t squared. I'm going to use this reference frame where x is pointing towards right. So therefore, v0 is minus 6 meters per second, and acceleration is plus 2 meters per second squared. So I said that the initial position is 0. I choose the origin in there. So the final position is 0. Initial velocity is minus 6. And the acceleration is plus 2. Okay. So as a result, the equation is t squared minus 6t. So that means there are these two solutions in here, two roots. First root is 0, and the second root is 6. Okay. I need to make a few comments in here, but let me just finish the problem. So there are these two solutions, and in that case, you have to use physics, some physical arguments to eliminate one of them and choose the other one. We eliminate the first one because this corresponds to the initial point. And as a result, we choose the second one because this corresponds to the final point. I mean, this must then correspond to the final point. Okay. All right. Again, you could have solved this problem in a different way. You could have found the final velocity as we are going to do in here. And you can use these kind of things. I don't know. There are different ways of thinking about it. So that's okay too. I think that's one of the comments that I have made earlier. So some people may tend to write not this equation, but they tend to write the equation with a minus sign in here, saying that the velocity is negative in here, right? That's the one that I ask you not to do, because formula is the same. It's just the velocity which is negative, right? We're not changing the formula, but the velocity, a negative value of velocity is inserted in here, right? So if you just look at it from this point of view, you will have less confusion later, okay? And that's why I'm stressing on this. Okay, what else? Yeah, that's it. Is there any question in here? I don't know. Yeah, probably there isn't. So let's then pass to part C. Okay, I'm asking for the final velocity. Now I can, since I know what the time is, I can use any of these formulas, right? V is equal to V0 plus A times T, for example, or I don't know. I mean, I can use other ones as well. Let me say etc. in here. However, I mean, let's just look at this problem from, again, this other point of view, right? Suppose that I didn't find the time. So suppose I didn't solve part B yet, okay? So the problem is this. I have an initial point in here. It's a constant acceleration motion. An object is passing from the initial point again as a second time. And I'm asking for the final velocity. So the initial velocity is known. And I'm asking for the final velocity. So what's the final velocity when the displacement is equal to 0? Okay, 2 points, 2 equations. I can use this one because since the displacement is equal to 0, this is a very special situation, all right? I can use this one. So in that case, since the displacement is 0, I get 0 in here. So that means the final velocity squared is equal to initial velocity squared. So that means the final velocity is plus minus V0. So there are these 2 solutions. One solution is that it says that the final velocity is equal to the initial velocity. You can check this with physics. And the other one says that final velocity is equal to minus V0. Again, you can check that with physics. So physically, this actually corresponds to the initial point. So I'm going to do the same thing as I have done in here with the time. So I had 2 time solutions. One of them corresponds to the initial point and one of them corresponds to the final point. And I have the same thing in here, right? I have 2 velocity solutions. One corresponds to the initial point and the other one corresponds to the final point. And I have to decide which one is which. So the first one corresponds to the initial point because V0 is the initial velocity. If both in magnitude and sign, all right? So because of that, I eliminated this, okay? So the point in here is this: in part B and C, there is this condition in here that I express in here, that the displacement is equal to 0. I mean, this happens twice in the motion of the object. Once at the initial time, and second time when it's passing through again. So as a result, when I insert in that condition, I always find two different solutions, right? One of them should always give me the initial condition, and as a result, I should eliminate this. And the other one should give me the solution that I'm looking for, okay? So as a result, then, therefore, the V is equal to minus V0 in here, right? The lesson is important, but this is kind of apparent in the graphical solution. In any case, let's say it like this. When the object is passing through the same point at a second time, it has the same speed, but velocity is in opposite direction. The velocity changes sign, right? That's basically what I'm saying, right? So initial velocity is V0, so therefore the final velocity is minus V0. Okay, that's essentially what I'm saying, right? Again, just I'm going to remind you that terminology. Speed is the magnitude. So the speed is the same at that point, but the velocities are different because they are in opposite directions. So the velocity changes sign. Okay. Another point of view, we can also think of it like that. Average velocity is delta x over delta t, right? So therefore, and again, one of the constant acceleration formulas says that the average velocity is equal to the arithmetic average of the initial and the final velocity. So in that case, the displacement is 0, so therefore the average velocity is 0. And so therefore from here you can basically says that the you can basically reach to the same conclusion again. All right, that's an alternative way of doing this. You might question why I didn't get the first solution, the initial condition. You could have gotten actually, but there's a slight problem in here. In that case, delta t would be 0, so you would get 0 over 0 in here. So somehow, naturally, we eliminate this kind of a case because we didn't want to compute 0 over 0. But I mean, if you have been, I don't know, if you have been following this thing, probably you should have also gotten the, you know that the first solution is there, but somehow you just eliminate it in here. Okay, so just think about this. All right, so let's continue. Right, a car traveling with 35 meters per second velocity to the right starts slowing down at a constant acceleration. And reduces, let's say, its speed to 25 meters per second in 5 seconds. What is the distance traveled by this time by in this time interval. All right, my English is not as good as it used to be. Like 25 years ago, I had the best English. So as a result, I'll be making lots of English mistakes in here, right? It's not that perfect now. So in any case, here the problem tells us the value of the initial velocity. So that's given. So let me just choose the x-axis in here. So there's this initial velocity in here, right, of the car. There's this final velocity. So the final velocity is so they are asking for the value of delta x, and the time is given, right? So v0 is given. So that's plus 35 meters per second. Final velocity is given, that's 25 meters per second, again positive. The time is given 5 seconds, and what's delta x? $150 meters, all right, yeah. Okay, so, I mean, let's just answer them. So some people have already given the answer. So in any case, I mean, you don't need to compute the acceleration in here. You just need to relate these three quantities. You just do this by computing the average velocity, right? Let's just say it like this. So the average velocity is 30 meters per second. And so as a result, the displacement is just the average velocity multiplied with the time. And so therefore, this is 30 times 5. So it's 150 meters with a positive sign. Okay. That's perfect then. In any case, some people in high school, they have learned this method as the graphical method, right? They just do it like this. So that's the velocity. They draw this thing in here, right? So the time is 5 seconds in here. So the initial velocity is 35 meters per second. Final velocity is 25 meters per second. And then they say that, well, the area in here is equal to delta x. So you just compute the area. How do you compute? Well, that's just a parallel trapezoid. So you just take the arithmetic average of the these two bases, which is v plus v0 over 2, and then multiply with the height in here, which is the time. Well, this is basically the same formula, right? You're doing the same thing in here. So it's this calculation in here, but you're just drawing some extra graphs in here and then trying to solve a geometric problem, right? Let me just say that. That's okay. I mean, you don't have to draw a graph for that, but if you want to draw a graph, that's okay. No problem with this. But it's not just the geometry. I mean, you're just actually doing this calculation in here. So you're multiplying the average velocity with time to find the displacement. But from the given information, you just compute the average velocity, right? So as a result, you can solve it easily. So this problem is the same as the previous problem, and it can be solved in the same way, right? So an object with, let's say, moving with constant acceleration has velocity 35 meters per second to the right. Let's say after 5 seconds, it is moving towards left with with speed 25 meters per second, right? And the geometry has changed a little bit. So there's this initial velocity in here, so that's v0. So I didn't say a car because, well, a car wouldn't do this motion. But in any case, later the object is seen to be observed to be moving towards left, all right? So the motion is something like this. So the object moves like that. Sorry about that. Moves like that and then turns somewhere and then goes back and whatever. Okay, it's the same kind of a problem, right? So the initial velocity is given. So I'm going to choose the x-axis to be right again. Initial velocity is given, so that's plus 35 meters per second. Final velocity is towards left, so therefore it's minus 25 meters per second. The time is given, so it's 5 seconds, and we need to find the displacement. Same problem. The only difference in here is that one of the velocities is opposite to the other one. Okay, so some people tend to solve this problem much more differently than this problem, but mathematically they are the same problem actually, right? It's just the sign of one of the quantities has changed. So a sign should not have such a cost actually. So you can solve the problem in the same way. So the average velocity is basically the arithmetic average of the initial and the final velocity. So therefore this is plus 35. I'm adding this with the final velocity, which is minus 25, and dividing with 2. So as a result, the average velocity is 5 meters per second. And so therefore the displacement is 25 meters in the positive direction. Okay. In the graphical method, so what people call as the graphical method. Okay. It looks like that. So this is the velocity versus time graph. So we have the initial velocity in here, v0, so that's 35 meters per second. And then there's this time in here, so that's 5 seconds. And this is the final velocity in here. So that's v is equal to minus 25 meters per second. So let me extend this axis like that, all right? Okay, so as a result, if you want to solve this problem with the graphical method, then you need to compute this area, count this area as negative and this as positive and subtract them. And well, to be able to do this, then you need to find what that time is, right? When I ask this problem, there's one homework problem in here, in the second homework. When I ask this problem, a lot of people actually solve it like that. They find this time in here. Let me kind of show it in the motion. So during the motion, there's this moment in here where the object instantaneously stops and then goes back. So that's the turning point. So they find the time of that turning point in here. So they divide the motion into these two parts where the object is moving towards right and then moving towards left. So they find this time, and then by using this time, they find this area, and then they find this and solve the problem. But that's unnecessary, right? This thing is basically not any different than a trapezoid. So that's actually a trapezoid as well. The only thing in here is that, sorry, I'm going to use a blue color in here. So that base of the trapezoid should be taken as positive, and that base of the trapezoid should be taken as negative. So, but still it's a trapezoid, right? You can think of it like that. So that's a positive base, so that's V0, and that's a negative base. So, right, let's say it like this. Take this base length as a negative number, right? So without computing this time in here, you can just compute the area by using the trapezoid formula, right? So you would just say that, well, it's basically the sum of the base lengths divided by 2. So that's the arithmetic average of these two base lengths multiplied with the height, and this is the height of the trapezoid. Height is equal to the time. So let me erase this. So multiplied with t, and so as a result, you get plus 25 meters, right? So you're going to get the same solution, but you have to extend your brain to these kind of geometric shapes where the side lengths can be negative. Okay, so think of it like this. I mean, you have been solving these trapezoid problems where both of these base lengths are positive. You have been solving these kind of trapezoid problems where both of these base lengths are negative in here. You have to extend your brain so that you actually solve the problems where one base length is positive and the other one is negative. It's just an extension of the same formula to a situation where, I mean, which is kind of logically reasonable, right? So the same formula should also apply in here. Okay. So as a result, I mean, when I'm asking these kind of questions, to discourage you from solving the problems like that, I give the numbers in such a way that this number in here, this time is here, as complicated as possible. But the final answer is very simple, right? Just keep this in mind. So as a result, I'm going to ask from you the exact displacement. Right. I mean, in any case, what I'm asking you is, don't think that, well, you know how to solve these kind of problems. Just look at these alternative ways of actually looking at the same problem, because sometimes these alternative methods might actually enable you to see some new things, right? So as a result, be open-minded all the time. Okay, so next, tomorrow, what I'm going to do, I'm just going to look at this freefall motion. Let me mention this, and then I'm going to add, stop here. So it's the freefall motion. I'm going to explain what it means. So it's basically the motion of objects which move only under the effect of gravity, right? That's the definition. You can think of it like this, which means no other force and no friction, no air friction, all right? So we will be talking about friction later, air friction later. Most of the time, for realistic problems, we are going to assume that the friction is negligible, right? Most of the time it is. And so as a result, just forget about the air friction in here. So again, look at the definition in here. So it's the motion only under the effect of gravity. So only the gravity is as acting. So as a result, I'm not actually saying whether the object is going up or going down. So in each case, I'm going to call this as a free fall motion, right? That's some kind of a convention with scientific terms. When I think of this as a term, scientific term, it has a precise definition, all right? It has a precise definition, and as a result, I accept only that definition. But apart from that, the term might have some other meanings, like falling has a definite meaning in everyday life. So as a result, no people actually will think that, well, an object which is going up is falling, right? They are going up. But scientifically, we don't look at the everyday language, all right? So we just look at the definition. So as a result, for us, an object which is going up is in free fall motion. All right. I will also say that, for example, the satellites are also in free fall motion as well. So as a result, think of it like this. So an object is thrown up. This is in free fall. Okay. Just keep this in mind, right? So in all of the scientific terms, we have this, right? So in any case, so that's some kind of a law that we are going to state later. So all objects in free fall have almost constant actually, but let's just say constant in here, constant acceleration. Let's say equal to the g gravity towards the center of Earth. So it's basically some magnitude and the direction as well. So gravity, of course, it has the value of 9.8 meters per second squared on Earth. But just keep in mind that in other places it might have, on the moon, for example, it might have other values. Since our purpose in here is to solve this problems, to understand the concept, most of the time we will be taking this approximate value of 10 meters per second squared. We don't want to struggle with multiplying numbers. So as a result, I will also keep on this habit. So as a result, I mean, tomorrow I'm just going to solve a few problems only by using this principle, and then I'll pass to the three-dimensional kinematics. Okay, so let me stop here. Sorry about being late in here, so I should have ended at 40 past, but